In this lecture, we will discuss replay mechanisms. Replay mechanisms are extremely important when we have aggressive speculation. Recall that aggressive speculation was predicting load values, addresses, load store dependencies, and all other forms of data and addresses which are typically not predicted. What I mean is typically not predicted in a simple pipeline, but it is necessary to predict them in an aggressive out of order pipeline. So sometimes in this prediction we'll make a mistake, and that is where replay mechanisms are required. Well, one option we have for doing a replay which is to flush the entire pipeline. However, flushing the pipeline for every single misspeculation is not particularly a very wise idea. The reason being that flushing the pipeline is very expensive for two reasons. So what are the overheads of doing a pipeline flush? So the first reason is that we need to clean up the state and we need to restore the state from where we are flushing. So essentially the restore and clean up actions take time. They are not instantaneous. So they take several cycles. But this again is not that much as compared to the sheer amount of wasted work, because what would happen is that we would have executed a lot of instructions and we simply stand to waste some work, right? So something that we would have gained had the speculation been correct, the entire work will be wasted, it needs to be redone. And a corollary of this of course is extra power consumption, right? Extra power or energy consumption. Well, extra power is not clear because we are flushing and restarting, but definitely it is extra energy consumption, which is an issue. So what we can do is, instead of flushing the entire pipeline, we can flush a part of the pipeline. So recall that this is a novel idea, we have not discussed this before. For flushing the entire pipeline, we did discuss the reorder buffer, but for flushing a part of the pipeline, this has not been discussed before. So what we do is that we somehow track all those instructions that have possibly used a wrong value and we re-execute only them. So we will revisit this notion several times, but essentially we re-execute a subset of instructions in the pipeline, right? We re-execute a subset. That is the crux of the discussion. So we replay those instructions once again after, let's say, the load completes its execution. When the instructions are being replayed, in this case they are guaranteed to use the correct speculated value. So let us say we are predicting the value of the load. So when instructions are being replayed, they are guaranteed to use the correct speculated value, they are guaranteed to use the correct value of the load. Because we detect a misspeculation when we realize that whatever we were guessing was not correct. So at this stage, what we do is that of course we initiate a replay, we will see how. We also wait for the correct value, and when that comes, we restart. So the next time we will not have a need to speculate. So what we want to do to kind of save wasted work and also not to avoid a full-scale pipeline flush is we need to locate what is called the forward slice of an instruction and just replay that. So let us define a forward slice. A forward slice is defined as follows. We have, let's say, one instruction I0, it produces a value. The consumers of those values are I1 and I2. So let's say I2, whatever I2 produces, nobody consumes it. But let's say I3 and I4 produce something, I4 consumes both, and so on and so forth. So we can create a graph of this type. So this will be what is called a DAG, or a directed acyclic graph, right? And so this is the structure. If you don't know what a directed acyclic graph is, this is the right time to actually look it up in a book on data structures, because this concept is used rather heavily in computer architecture. So you cannot escape this concept. So it is far better to look it up right now. So this structure that we have here, note, is not a tree, right? So this is not a tree. So let me do this. It is a directed acyclic graph. And furthermore, this is rooted at the instruction whose value we are predicting, right? It is rooted over here. So this entire set of instructions is known as the forward slice of instruction I0. It contains the instructions consumers, its consumers, and so on. So the entire forward slice, including I0 and all its consumers, and so on, the forward slice has to be replayed, but not the rest of the instructions. For example, it is possible that another instruction was issued along with I0, but it is independent from I0, and even some of its instructions are independent, not in the forward slice. So this set of instructions can execute, and it should also be allowed that these instructions execute, but of course the commit happens in program order still, but at least these instructions are not re-executed. Only the forward slice is the candidate for replay or re-execution. So the trivial solution could be that we flush the entire pipeline, or somehow we flush the pipeline between the dispatch and execute stages if it is doable. But this again is wrong and impractical and hard to implement. So we should go for a smarter solution, which is non-selective replay. So we will discuss three replay schemes: non-selective replay, a delayed replay, and a token-based replay. So this is the first such scheme. So this scheme is simple, but as we shall see, there are some issues, but the issues can be fixed. These are not major issues, so these are all fixable issues. So the first is that it is not really necessary to flush or remove all the instructions. So I would not call it schedule, let me call it dispatch. So between the dispatch and execute stages, all the instructions that are there, right, which could potentially be consumers, and so on, we don't have to remove all of them, alright. So even if they are in the window, they can be there. We don't have to remove all. That's the first insight. So we can be slightly prudent and judicious about it. What we can do is we can reduce the set of instructions and only focus on a set of instructions that have possibly gotten the wrong value, right, because of the misspeculation. So what we do is we define what is called a window of vulnerability, WV, that's its abbreviation, which is the window is n cycles after a load is selected. Alright. This window of n cycles is known as the window of vulnerability. So let's say that the load is selected in cycle number 0. So what we do is that we consider a window of n cycles after it, right, till the nth cycle. So this entire period is known as the So how do we determine n? Well, n is determined based on the predicted latency. So for example, let's say we are predicting that the load will hit in the data cache. So then what we do is that if we are selecting in the 0th cycle, in the first cycle we will read the register file. In the second cycle we will compute the address, and after that in the third and fourth cycle, assuming a 2-cycle latency for accessing the data cache, at the end of the fourth cycle we will get to know if the value is there or not in the data cache. So if we expect that a given load will hit in the data cache, which means it will be found, then we can set the window of vulnerability equal to 4, or we can set n is equal to 4 over here, and within this period we expect that the value will be available. If it is not available, then of course a replay has to be initiated. So this means that the load will take more than n cycles, and this is where a replay definitely has to be initiated. So the reason that the window of vulnerability is defined defined in this manner is basically because any instruction that is waking up, let me change that to say that any operand that is waking up during this period in the window of vulnerability might have been woken up speculatively, because it might get selected, it might go down the pipeline, and it might not find its value. So we should particularly be interested in those instructions whose operands are woken up in this period. Let us consider the example of a speculation. So let us assume that we have a load instruction. The load instruction loads from this address. The address is stored in register R2. Furthermore, assume that we predict the value. The predicted value is stored in register R1, which is the destination register of the load. Now let us consider these three instructions. Instructions 2, 3 and 4, which have had at least one operand that wakes up in the window of vulnerability of instruction 1. So one thing that is obvious is that register R1 will clearly wake up because it is in the WB of instruction 1. But let's assume that the other two instructions also wake up because of other broadcasts, right? So we will discuss this issue later. But for the time being, let's assume that that instructions 2, 3 and 4 are within the window of vulnerability of instruction 1. So if there is a misspeculation, what will happen is that we will squash. What does squashing mean? That we will essentially set them from ready to not ready, right? So we will in a sense kill their readiness. That is called squashing. So we will squash these three instructions, right? And then we will wait for instruction 1 to get the correct value, which is the correct value of R1. We will reissue it, and then we need to reissue these three instructions once again to the pipeline. So it is possible there are two cases. One is that the operand woke up, but the instruction was not selected. So instruction is still in the instruction window. That is one case. The other case is that it was selected and it has been sent down the pipeline. That's the other case. Regardless of the case, in both cases we squash them and we reissue. So how exactly is this done? Well, the way that this is done is that the instruction window entry for every operand is augmented with some additional circuitry. What is that additional circuitry? Well, the additional circuitry is that we store the tag over here. So the tag is the tag that we are expecting from the tag bus, or we can say that this is, let's say, a source operand. Can be source operand 1 or 2, doesn't matter. So the tag goes here from the tag bus. If there is an equality, we set the ready bit. So this part we have already seen because it was a part of the instruction window, right? So there is nothing new over here. But what is new is that in addition to these two, the tag and ready bit, we have a timer, right? So the timer is basically a simple piece of logic and state where once the operand wakes up, not the instruction, once the operand wakes up, we set the value of the timer to n, right? So this is a capital N, small n here, so kindly ignore that. So regardless of, whether it's lowercase or uppercase, we set the value of the timer to n, and every cycle it decrements n, n minus 1, n minus 2, so on until it reaches 0. So every cycle we decrement the timer. Once the value of the timer becomes equal to 0, we can conclude that the window of vulnerability is over, right? It is not a part of the window of vulnerability, and we can conclude that this instruction will not be squashed. Alright. So what happens? So what happens is that we augment every instruction window entry, particularly the entry for the source operand with a timer. Once the operand wakes up because of a broadcast, we set the timer to n, and subsequently in every cycle we decrement the timer. And if, let's say, it receives what is called a kill, so I'll discuss what is a kill in 1 second. When the timer is non-zero, then we squash the instruction, which means we set the ready bit back to 0. So how do we actually squash an instruction? So what we do is that we assert the kill wire. So the kill wire is meant to go and kill all those instructions whose timer is not equal to 0. So for the timer, we have a little bit of additional circuitry over here. So there's a logic block, I'm not showing that. This is 1 if the timer is non-zero, else 0. So assume the timer is non-zero. So this is 1, and if the kill wire is 1, this is 1. This is a NAND gate. So the output of the NAND gate is 0. So pretty much the ready bit gets set to 0. And also the timer gets set to 0, in the sense the timer also gets reset. Alright. So that's the important thing, that both the timer and the ready bit both get reset if we are asserting the kill wire. So the kill wire essentially says that, look, go through all the operands in the instruction window. For any of the operands, if the timer is non-zero, then set its ready bit to 0, which means that squash it, right? So which means that the operand becomes non-ready and the instruction hence becomes non-ready, right, if there is such a word. Alright, so this is the basic broad idea of the non-selective replay scheme. So non-selective replay scheme kind of doesn't look at whether the instruction is in the forward slice or not, but straightforward goes and does this. So what is the key idea of the non-selective replay scheme? The key idea of this scheme is that we assert the kill wire when we detect a misspeculation, and the kill wire then goes and does this, right, via this logic, which is a NAND gate. So let us now look at all of those entries for which the timer is 0. So I have not discussed that case. So in that case, what will happen is that if the timer is 0, regardless of the kill wire, this will be 1. Alright, because the NAND gate, if any one of the inputs is 0, the output is 1. So this is a special piece of logic where essentially what happens is that if the output is 1, we actually, for this piece of logic, if the input is 1, we don't do anything. In a sense, we don't touch the timer, we don't touch the ready bit. So pretty much this circuit gets inactivated if the input is 1. So recall that for both of these logic blocks, it's the same input. So if it's 1, we don't do anything. Only if it becomes 0, right? Which is if both the kill wire is asserted and the timer is non-zero. In that case, what we do is that this is when this circuit gets activated. So it sets the ready bit to 0 and it resets the timer. So how do we do this? Well, with each instruction, if there is speculation, we attach the expected latency, which is essentially the value of n. Let's say there is an additional delay, in the sense this threshold of n gets breached. Maybe because we are doing latency speculation and we predict that it will hit in the D cache, but it actually misses in the data cache. In that case, it is a time for a replay. So what do we do? Well, as you can see the monster over here, we assert the kill wire. So each instruction window entry will have a non-zero timer. That has a non-zero timer will reset this ready flag, which basically means a squash, right? So this is happening at the operand level, not at the instruction level. So we now have a set of instructions that need to be replayed. How do we replay? Well, we will discuss this in the next 2 slides where we discuss methods of replay. So the simple method of replaying, which we call method 1, is keep instructions that have already been issued, in the sense that they have left the instruction window because they were woken up and selected. We still keep them in the instruction window, right? So we don't remove them. So in our simple version of the pipeline, when they got selected, so what is issue again? Well, issue let us define as the entire process of wake up and select. So right after which it goes to the execution units. So if it hasn't been issued, which means it's still lying around in the instruction window, then there is no problem. But if it has been issued, we still keep it in the instruction window. We let the instruction flow through the pipeline stages, and then we verify. How we will verify? Well, we will discuss, it is different for different schemes, but at least for this specific scheme, what we will do is that we can definitely verify for the load instruction if its speculation has been correct or not. For the instructions in the forward slice that have been issued, there is no quick fire way of verifying right now, but that doesn't matter. For any issued instruction, once the timers for all of its operands become 0, it can be removed from the instruction window. So this we can treat as verification. So what we can do is that for this particular scheme, so of course for other schemes it will differ, but for this particular scheme, any issued instruction if the window of vulnerability has passed, which means the timers are 0, for all of its source operands, it is verified. So we can have a small separate circuit to check that, right? Or periodically we can check. So it depends on the implementation. So as I said, we can either have a periodic pass that every 10 cycles we look at all of the instructions that have been issued, and they are not within the window of vulnerability. None of their operands are within the window of vulnerability. They can be removed. So whatever logic we choose, this is the verification logic that an instruction has correctly executed for this particular scheme. So as I said, it will vary depending on the scheme, but regardless of this, we have a generic verification conceptual block over here, and once an instruction is verified to be correct, it can be removed from the instruction window. So this is one approach. The other approach that we are calling method 2 is that we move the instructions to a dedicated replay queue after issue. So after we issue, we remove the instruction and we move the instruction to a dedicated replay queue. So as the instruction moves to the pipeline stages after the instruction window, we also send it to a dedicated replay queue. And the verification logic is the same. So assume that it gets verified, which means that there is no misspeculation, it's not in the forward slice of any misspeculated instruction. Then what we do is that we remove from the replay queue if verified. Alright, so we just remove it, throw it out. And let's say if there is a replay, then instructions from the replay queue will enter the pipeline via this mux. Alright. So the replay queue does two things. It is a temporary storage area for instructions that have been issued but not yet verified to be fully correct. Fully correct basically means that they are not in the forward slice of any misspeculated instruction. So this is a temporary staging area, Once they are verified, they are removed. And if we need to do a replay, then from the replay queue, we can replay these instructions like this. That is why a multiplexer has been provided. So this replay question we didn't answer for the previous design, which is method 1. So I will start by first erasing the ink on the slide and then telling you that if we have to do a replay, then what will happen is that since the instructions that need to be replayed are already there in the instruction window, they will simply proceed to the rest of the pipeline stages instead of the instructions that are not being replayed. So we'll give higher priority to the replay instructions, the instructions that are being replayed, and they will move through the pipeline stages, and this time the verification will be successful because they are guaranteed to be on the forward slice of at least that misspeculated load. Right, so in this case, the temporary staging area is within the instruction window, and they don't leave the instruction window unless it is guaranteed that they will never uh, be a part of a misspeculation, and the replay proceeds from here, whereas in this case the replay proceeds from a dedicated replay queue. So in most designs this is kind of preferred because it is simpler, it is more scalable, it's easy to create it in hardware, and also there is no need to increase the complexity of the instruction window given that it is so complex as it is, right? So we made it even more complex with this mechanism. So typically using the replay queue is more common, but again I don't want to take sides. For the purposes of simplicity, the instruction window can also be used. Now we need to discuss one important corner case with the non-selective replay scheme. So let us look at this scheme in somewhat more detail. Let us now look at a very important corner case. So this corner case is present in a lot of replay schemes that consider a superset of the forward slice, and clearly one such scheme is this scheme, the non-selective replay scheme. So in this case, this is the first instruction that we are speculating, and we are speculating, let's say, the value of the load, which is the value that will be loaded into register R1. Let us further assume that these three instructions are in the window of vulnerability. So these three instructions will get squashed. So let us say you assume that whatever speculation you are doing, either the latency or the value, it doesn't matter. But the speculation is that within a certain time period, the value will be there with us. If this is not happening, let's say for a cache miss, the add, sub and XOR instructions will need to be squashed and subsequently replayed. So one thing that is rather clear is that the add and sub instructions, the tag will be broadcast and they will be replayed in the natural course of actions. Why? Well, we can clearly see a dependence. This is the WV instructions, and R1 is basically the value whose tag will be broadcast, is the register whose tag will be broadcast. So the second instruction over here, the add instruction, both of its source operands are R1. We can clearly see a read after write dependence over here. Now if we take a look at the next instruction, then that would be reading R2. Again there is a read after write dependence. So we can clearly see that instruction 1 will wake up instruction 2, which will wake up instruction 3. But here is the fun part, that the XOR instruction, XOR R5, R6, R7, the XOR instruction is independent of the first three instructions. So there is clearly no read after write dependence. As a result, in the entire forward slice of the load, the XOR instruction is not there. So it is one of those instructions that is a part of the WV but not a part of the forward slice of instruction 1. So in a certain sense, if for some reason this gets squashed, why will it get squashed? Well, it is possible that uh, the operand, the source operand corresponding to R7, that was woken up in the window of vulnerability. Now the ready bit of this will be set to 0, and as we can see, there is nobody to set the ready bit of R7 to 1, which essentially means that there is nobody to wake up the XOR instruction, right? And so of course I didn't see the example here, so instead of R7 it considers R6. So it says that let's assume, so let me go by what is written. So let us assume that R6's ready bit is set to 0. Then as we can see, no other instruction before it is actually writing to R6. So it is very well possible that one of the early instructions that let's say was writing to R6, that is committed and left the pipeline. After that, there is no instruction to broadcast the tag associated with this register. Hence, this instruction will become an orphan. There is nobody to wake it up. And unless we do something, it will remain in the pipeline forever. So this needs to be understood, that this instruction over here is an orphan. We require another instruction to wake it up. That other instruction, there is a possibility that it might not be there. If that is happening, then this instruction will stay in our pipeline forever. So we have to deal with orphan instructions. And why do we have orphan instructions? Well, we have them because our window of vulnerability, let's say all the instructions that were squashed in the window of vulnerability are essentially a superset of the forward slice. Right, so it can be superset or it can be equal, right, of the forward slice, and this is causing the problem. So there are two ways of solving this. The first is an impractical method, but it nevertheless should be discussed because it is the classic example of a bad idea. So in this case, what we can do is we can devise a mechanism to keep track of the squashed instructions. One way of keeping track of the squashed instructions can be that we have some auxiliary structure that is some kind of an appendage with the instruction window. So what we do is that whenever we squash instructions, whenever we squash instructions within the instruction window, we transfer them, we essentially copy their IDs to an auxiliary structure, and then basically we detect which ones are a part of the forward slice and which ones are not, and then we can identify the orphan instructions and then rebroadcast their tags to wake them up, or not kill them in the first place, right? So even if let's say they have been their operands have been set from ready to non-ready, right, from 1 to 0, we can convert it to 0 to 1 if they have already been issued and remove them from the instruction window at a later point in time. So even though having this auxiliary structure that can be used to temporarily store some of the instructions that have been squashed, that appears to be a feasible idea, but this is very hard to implement, right? So this can be attempted as long as somebody is willing to do it and implement it correctly. But a far better approach, which is simpler, right? I am only stressing about simplicity here, is that we let the orphan instruction reach the head of the ROB. So if we don't do anything, then the orphan instruction will reach the head of the ROB. At that point, we will find that this instruction is an orphan and it is essentially waiting for a register operand, which clearly means that it has been squashed, right? So at the instruction, the head of the ROB, cannot wait for a register operand. Alright, and the only thing that it can wait for is that it can wait for some value to come back from memory, but it clearly cannot wait for, let's say, the result of an add, subtract, or multiply instruction. At that point, we can execute and commit it. Alright. So this is, if you think about it, this is something that does give us some simplicity. Of course, we do sacrifice a little bit of ILP because of it, because we could have executed this, we could have woken up its consumers and done a lot, we are not doing it. So there is clearly a trade-off, and something in the middle is also possible, where maybe we let the orphan instruction reach a certain point in the ROB and then we initiate a check. So it is doable, but as I said that creating orphan instructions as it is, either as they are, that is a problem, right? So we should try to create as few of these as possible. So let's now look at another method that tries to reduce the number of orphan instructions and is more efficient. So this method is known as delayed selective replay. So here the idea is to replay only those instructions that are in the forward slice of the misspeculated load. Right? They are the only ones that are executed once again, and the rest are pretty much allowed to go through. We will see how. Right? So here also orphan instructions are created, but we will have a new method, a different method of actually dealing with them. So let us extend the basic non-selective replay scheme. So we will still have the non-selective replay scheme with all of its elements, and the elements will be the kill signal will be there, the window of vulnerability will be there, everything will be there. But what we will do is that we will have something extra, right? And this extra is what gives this scheme its edge, its advantage over the previous scheme. So in this case, whenever we detect a misspeculation, what we do is, along with asserting the kill signal, we plant a poison bit in the destination register of the load. So the destination register, instead of containing 64 bits, in this case contains 64 plus 1 bit, and this bit is known as the poison bit, and this poison bit is set to 1. So wherever the value is stored, this includes the register file. Wherever the value is transmitted, this includes the bypass paths. We increase the width of the data path from 64 to 65 bits, and we also say that, look, this is a value which has been poisoned. So what we do is that we propagate this bit along the bypass path and the register file. So then in this case, what happens is, let's say that we predicted that a load will hit in the data cache, right? So let's assume we did that. And let's assume that after n cycles, we find out that the load value will not come from the data cache, it will come from somewhere else. So what we do is that we basically create a dummy value, which is, the dummy value has no meaning, right? So this value is created, and along with that, we set the poison bit to 1. We write this dummy value to the register file, and we also broadcast this dummy value on the bypass paths. What is the need for doing it? Well, the need for doing it is that we would have speculatively woken up instructions. So we would have speculatively woken up consumer instructions, and those consumer instructions maybe would have gotten selected, maybe would have proceeded down the pipeline. So they will anyway read the register file. Alright. So if they read the register file, instead of reading an erroneous value, it is far better that they read a value where the poison bit is explicitly set. So then what happens is that if an instruction reads any operand, either from the bypass path or from the register file whose poison bit is set, then the instructions poison bit is set, and then it kind of propagates it. So its destination registers poison bit is set, right? Uh, so basically what happens is that the poison bit propagates, right, via the instruction, uh, the, the instructions destination register. It is passed to the consumer, consumers, and so on. So let me give an example. Let us say that we have a load instruction, and this load has a misspeculation. So we set the poison bit of this. Then if we have an add instruction of this form, then we set the poison bit of R2 because it is reading R1. Then if we have a subtract instruction of this form, we set the poison bit of R3 because it is reading R2, so on and so forth. So pretty much along the forward slice, all the values get poisoned. So which basically says that all of these values are in a sense invalid. They are potentially wrong. And we say that all these values are poisoned. So this is one way of nicely keeping track of the forward slice. It has its issues, but at least you can see that a bit is being propagated along the forward slice of this instruction. So what do we need to do in terms of changes to the pipeline? So when an instruction finishes execution, we check if its poison bit is set, which means after the EX stage, right? So after the EX stage, recall that we actually set a bit in the ROB indicating the fact that the instruction has completed its execution, right? At this point, we check if its poison bit is set. If yes, we squash it, right? So squashing it would basically mean that we set the ready bits in the instruction window to 0, and we also stop ourselves from setting the ready bit in the ROB, the instruction completed bit in the ROB, right? We don't set that. So we basically squash it, which essentially means that this instruction is not completed. If we go back to the replay queue where we talked about a verify logic, we can add one more verify stage over here where it will verify this poison bit, and if it is set, well, then the instruction remains in the replay queue. It doesn't go anywhere. Otherwise, we just remove it. We remove the instruction from the IW or the replay queue depending upon which scheme, which replay scheme we are using. So what are the issues with the scheme? Well, this scheme is effective in the sense that as long as we know the value of n, which we may not know all the time, but as long as we know the value, which is true most of the time, the scheme is undoubtedly effective. So now it is important to understand where do the advantages lie. Well, the advantages lie in the fact that if we consider the two kinds of instructions that are in the WV but not in the forward slice, then we can see that at least one of the kinds will benefit. So let me kind of explain this in a different manner. So let me consider all the instructions which were there in the window of vulnerability but were not there in the forward slice, right? So let me consider the difference. So these instructions ideally should not have been squashed. But since we do not explicitly have a mechanism of maintaining the forward slice, well, we still need this. Now what we do is that we can divide these into two types. One type, let's say, would have issued. One type would have not issued. So if I consider all the instructions that would have issued, then we would have cleared them, right? So why would we have cleared them? Well, we would have cleared them because we would have seen clearly that their poison bits were set equal to 0. So the instructions were clean, they would have gone through. So this would have reduced the number of orphan instructions right here because this set would have been treated correctly. What about the other set of instructions which are there in the window of vulnerability, but let's say for some reason were not issued for a long period of time? So even after the window of vulnerability, these were not issued. It is very much possible that because of the kill wire, one of their operands got invalidated, right? So we need to worry about this set, not about the other set. So if I were to consider this set of the instructions which are there in the WV, the window of vulnerability, but those who have not issued, they can become orphans. And if they become orphans, we'll have a similar problem, right? So what we can do is we can always wait for the instruction to reach the head of the reorder buffer. And at that point of time, we can say that, look, this instruction is indeed an orphan, so we can execute it. But what was done in this paper, which originally suggested this scheme, is that they looked at a different idea. They introduced a different mechanism, which as you will see is effective. So all such mechanisms do add their hardware overhead, but they are indeed effective. So let's say instruction J was orphaned because of one of its operands, which was woken up by instruction K, was reset back to a non-ready state. So J is the one that is getting orphaned. It is getting orphaned because one of its source operands, the ready bit of that was set from 1 to 0. And originally instruction K, which was clearly before J in the instruction sequence, had set the ready bit of the operand S1 to 1. So let us look at this on the timeline. Okay. So what would happen is that instruction I will broadcast its tag and it will say that, look, I have been selected. It will do an early broadcast of its tag. Alright. Then what will happen is that in this case, n cycles later, we will detect that there is a misspeculation for instruction I. So we will assert the kill wire, right? In the middle, what will happen is that instruction K will broadcast and one of J's operands will, this source operand, its ready bit will get set, right? So then, I'm assuming it gets broadcasted and then subsequently J's operand wakes up. Right, and after J's operand wakes up, J is kind of ready to get selected subject to its other operand. But let's assume that it doesn't get selected, it remains within the window. After the n cycle, after the window of vulnerability is over, because one of J's operands is vulnerable, it gets set from 1 to 0. Well, no problem. So what you will see is, we can add one more bus where instruction K will come back later to rescue instruction J. So instruction K will again wait for n cycles. So instruction K of course has broadcast and gone away, but after n cycles a timer will elapse. Instruction K will broadcast the tag once again on the completion bus. So this is one way for instruction K to actually rescue all of those instructions like J which it had woken up, right? So what does instruction K do? It actually broadcasts twice. It broadcasts once at this point of time, which is its regular broadcast, and then it broadcasts once again, which is n cycles later. In this case, it is a new broadcast, it's a fresh broadcast. It is not something that was there in an earlier scheme. So we are assuming that along with the tag bus, we add another bus called the completion bus, in which the second broadcast is made. And in that, again, the ready bit of this operand S1 is set from 0 to 1, and instruction J can proceed subject to the ready bits of other operands. So this is one example of a repeated broadcast where you kind of come back and rescue those instructions which for some reason have kind of fallen in the shadows of some window of vulnerability, and who have kind of from a ready have gone to a non-ready state. So this is one way of taking care of operands. As you can see in this method, the important operative point over here is that in this method, because of the poison bit, we were able to kind of split the potentially orphaned instructions, which is this set, into issued and not issued. Issued instructions, no problem, their poison bit will not be set. Not issued instructions, we can either have the default scheme, which is wait for them to reach the head of the ROB, or otherwise, what we do is we have this repeated broadcast scheme to rescue them later. Alright. Now let us have a slightly deeper discussion about the scheme and discuss a few of the subtle points which would kind of tell you about some of the intricacies of having such schemes and implementing a replay scheme in practice. Let us now discuss a few subtle problems that will happen while constructing the window of vulnerability. So what was discussed in the lecture on non-selective replay was that the window of vulnerability starts when we select the instruction. That is not wrong. Turns out we can do better. So consider this cycle, this instant of time when the producer broadcasts. So this pretty much tells the rest of the world, particularly the consumers, about the existence of the producer, about the fact that it is broadcasting its tag, right? So it tells the consumers that look, this is when you can get yourself selected and you can enter the pipeline. You'll get the value either from the register file or the bypass path. After that, the producer executes other stages like reading from the register file, execution, and so on, and then at one point of time the execution completes. Now from the point of view of a consumer, it is essentially this point of time that is important. So we assume that in this cycle either the execution completes or we are aware that the execution will not complete. So we assert the kill wire. Right? So either one of these two events happen. Now from the point of view of the consumer, when it receives the broadcast, let us say that it gets selected in the same cycle. So in this cycle, if it is getting selected, then it needs to set its timer equal to n, let's say. And in this cycle, when it may receive the kill signal, it sets its timer equal to 1, right? And its timer should be equal to 1. And of course, in a realistic pipeline, sometimes the latency might be variable. So this might be the latest possible time at which we will get the value of the kill signal, right? It could be the latest possible time at which the value of the kill signal will be gotten. So then if let's say we get the kill signal at any earlier point of time, then of course the value over here will be nevertheless greater than or equal to 0, right? Because the value of the timer at the latest possible time is equal to 1. So for us, this should be the window of vulnerability, which pretty much starts with the producer actually broadcasting. Alright. So this is a slightly more accurate way of doing it as compared to when it can be at other points as well. It can be when the producer is selected, for example. So even that would not be wrong. So if I were to consider the select point, which is an earlier point, and define the window like this, so it is possible that n will be higher, it will be greater than what it actually should be, which means that the WV will slightly extend to the right. So this will just produce more squashes, more orphan instructions. It will not be wrong. So the correctness criteria over here is that we should not allow an instruction to complete if it should be squashed. In the sense, it should not be getting a wrong value. So this is one aspect, one subtle aspect of the timing. Another question that many times students ask is that, why have poison bits in the delayed selective replay scheme? Why have poison bits and the WV together at the same time? What is the advantage of doing that? Well, if I just have poison bits, just think about it. The forward slice can just become huge, in the sense the forward slice will never terminate, right? So let's see, if I have one load instruction, its value will be poisoned, then so on and so forth, right? It will just keep going on and on and on. After a certain point, of course, the correct value of the register R1 will come, and after the correct value of register R1 comes, again we'll start re-executing them. But this forward slice will actually become very large and it will just keep on growing. So the size of the forward slice has to be limited. So one way of limiting the size of the forward slice is to essentially draw a line, which is the line at the end of the window of vulnerability, which is drawn by setting the kill wire, right? So this is drawn by setting the kill wire. So in the kill wire, what happens is that it abruptly terminates the forward slice. So it doesn't allow the forward slice to increase, because all the instructions that are in the forward slice with operands that wake up during the window of vulnerability, if they have not been issued, they pretty much get killed. So this limits the size of the forward slice. It can't grow any further, and whatever few orphan instructions are there, they can be taken care of. If we just have poison bits, and if we don't do something extra, which we will see in the token based replay scheme, the size of the forward slice will become huge. So the WV in a sense limits that, and hence it is required. So for us, the direction is to have something that exclusively uses poison bits, but we will show that one bit is not enough, we need more bits. So there are two things. So we will show that, look, one bit is not enough because it is not distinguishing between the forward slices of different loads, because we might be speculating different loads at the same point of time, right? And the other is that we need to make changes at the level of the rename table. Making changes at the level of the instruction window is not good enough. So with this, we will proceed to the next scheme that uses token based replay. So let us now look at token based selective replay, which extends the idea of poison bits. So let us first leverage a pattern that is found in most programs. So what we see is most of the misses in the data cache are accounted for by a very small number of instructions. So typically the 90-10 thumb rule is followed, where 90% of the misses are accounted for by only 10% of the instructions. Again, 90-10 is not a hard and fast rule. It can be 80-20, but you roughly get the sense that most of the misses are accounted for by a minority of instructions. So we can design a predictor where, given the PC, the program counter, we predict if it will lead to a data cache miss or not. Correct? So given a PC, we predict whether it will lead to a miss or not. And we use a predictor similar to a branch predictor. We call this a hit-miss predictor at the so similar to the branch predictor at the fetch stage, this predictor can be there at, let's say, the decode stage. Once we know it's a load or store, and let's say for loads, we can use this predictor and we can predict if it is predicted to hit or miss. So what do? What we do is that we have a hit-miss prediction that is similar in principle to a branch predictor, and that gives us a good idea of whether we will hit or miss, right? So instructions that are predicted to miss will have a non-deterministic execution time most likely and will lead to replays. So let us call this set S1, right? So most likely these instructions will lead to replays. Other instructions will most likely not lead to replays, the ones that are predicted to hit. So let us call this set S2, right? So let us consider the set S1. So these instructions is where we would want to do some kind of latency speculation or value speculation, some kind of prediction basically, all right? So if we do some kind of prediction, and so since there is a high likelihood that things can go wrong, we will have to provision for replays. So let the instruction collect a free token. I'll discuss in a second what a token is at decode time. And we save the ID of the token in the instruction packet. So essentially a token is a number. So let's say if we have 10 tokens, the tokens can be numbered 0, 1, 2. So we can take any free token, let's say token number 2, and this for us is the token. So we will have a dedicated token allocator similar to a free list that will allocate a token to the instruction which we are predicting to have a problem. It might need a replay. And instead of a hit miss predictor, if there is a different kind of speculation, we can also use a confidence predictor where, let's say if it is low confidence, then we can either decide not to speculate, or if we are speculating, we should provision for a replay. So we give it a token. So assume the instruction load R1 4R4 is predicted to miss. So then what we do is we give it a token and we save the ID of the token in the instruction packet of this instruction, right, as well as in other places, but let's first we store it in the instruction packet, and we say that this instruction is the token head for the token it collected. So if it, let's say it has collected token number 5, we say that it is the token head for token number 5. Alright, so that's what we say. So then what we do is that we propagate this information to all the instructions that are dependent on the load, which is similar to the way that we were propagating poison bits to the consumer, consumer's consumer, and so on, such that the entire forward slice will have token number 5. So the load of course will have it, and the entire forward slice of the load will also have token number 5. Alright, so this can be propagated. So now if the load instruction fails, in the sense that let's say we were speculating that we made a guess that it will hit in the D cache, and then we did an early wake up for other instructions, and as we had predicted there might be a problem, and there was a problem. So it is very easy to identify the forward slice of the load instruction just by this token ID. We can just squash them. We will see how. This is just a high level idea. So what we do is, to implement this, we change the structure of the rename table. So we had discussed this load instruction, right? So in the rename table, given a register as input, an architectural register as input, the rename table previously was yielding only the physical register, and of course the available bit, but I'm not talking about that right now. Along with that, let us also store a token vector, which is a bit vector of tokens. And let's say if token number 5 a given instruction has, so we number the bits 0, 1, 2, 3, 4 and 5, and if it contains token 5, there is a 1 here. It can also contain multiple tokens. If it contains token 2, there is a 1 here. The rest are 0. So if an instruction is a token head, we will save the ID of the token that it owns in the instruction packet. We have already seen that. We assume that we have a maximum of n tokens, and token vec is an n-bit vector, which means that this vector is n bits. For the instruction that is the token head, so what we will do is that we will have a token associated here with each source register, and we'll also have a token vector associated. We'll have a token vector associated with each source register, and we'll have a token vector associated with the instruction. So consider any instruction of, let's say, this type. So for R2 and R3, we access the rename table. So let's say the token vector that we get is T2. Then for R3, we get T3, right? Then the tokens that R1 will contain, which is also the same token that the instruction will contain, will be T2 union T3, which means that it is a part of the forward slice of both the instruction that produces R2 and the instruction that produces R3. Alright? And of course, now these are all the tokens that R1 contains. So any subsequent instruction that uses R1, right, that will automatically inherit all the tokens that R1 contains. So tokens are propagated in that fashion. Now if we consider a load instruction of this type, well then the tokens that R1 will contain will be the token that was assigned to R1 because it's a token head, which let that be T, union the tokens of R4, let us call it T4, right? So this will essentially be the tokens corresponding to the load instruction as well as the destination register of the load instruction. So this is shown nicely in a diagram over here. Let us assume that for R2 and R3, these are the tokens shown with different colors. So when we add R1, R2, R3, the tokens for the instruction as well as the tokens for the register R1 are basically these. So you can see that all of these tokens show up here. It is a clear union operation that we have, right? So then what we do is that in the rename table, we read the tokens for R2, we read the tokens for R3, we perform the union operation, and then again we write back the tokens for R1. And of course, let's say if this were a load instruction and there was a token head, we would add that also, and that would be the tokens of R1. So what do we again do? We read the token vecs of the source operands from the RAT table. So the RAT table is again being made more complicated. So in any architectural scheme, some of these structures, have to be made more complicated. We merge the token vecs of the source operands, as you can see. We save the merged token vec for the destination registered in the rename table, as you can see. Additionally, this is also stored in the instruction packet such that later on in the pipeline, this information can be used. So here, what is the key insight? The key insight is that instead of having one poison bit, we actually have many poison bits. So previously in the delayed selective replay scheme, we had one poison bit. We don't have that here. We have many poison bits, right? Not one. We have many poison bits and each one of them is a token and they are propagated. So after the token head instruction completes execution, so after the load instruction in this case, we see if it took additional cycles. So this is essentially the verification phase that we have been talking about. If yes, well, then it means that we have a problem. So we broadcast the token ID. So token ID is the ID of the token head to signal a replay, which is case 1. And as you can see, let us say that this was the token head of the load instruction. It is broadcasted and this signals a replay for these two instructions. Case 2 is that no problem happened. Then we broadcast the token ID to all the instructions. They turn the corresponding bit off. Right, so sorry, I should have shown this animation. So I'm clearing off the pointer and I'm showing this once again, that we broadcast the token ID and we replay these two instructions. But if there is no problem, which is the second case, then we can turn the corresponding bit off, which as you can see over here, that we broadcast it to all the instructions in the instruction window. And as I said, the token vec is a part of the instruction packet and we will also store it within the entry of each instruction window. So once we broadcast it to all the entries of the instruction window and the rename table, all of them will turn this off. So as far as we are concerned, the token is released, right? So this was one problem we were having in the earlier case, right? That forward slices used to grow and grow. So this will not happen. As soon as the token head instruction has executed correctly, we will just release the token. But for that, first we will have to broadcast it to all the entries in the instruction window and rename table such that they set the corresponding bit associated with the token to 0, and then the token can be added to the free list of tokens. So this was for the instructions in which we are predicting a problem. We made a provision for a replay. S2 is the set of instructions for which we were not predicting a problem. Like for example, if we are doing a latency speculation, we are predicting that for S2, there is a very high likelihood that they will hit in the cache. But then nevertheless, it is a predictor. So assume an instruction that was not predicted to miss actually misses. Well, no token is attached to it. We have not attached a token. So the only thing that can be done is we adopt the more expensive option over here, which is to flush the pipeline. Alright, so we have had a fairly deep discussion of replay based mechanisms. So we will stop this lecture video over here. The next lecture video will look at a simpler version of an out of order pipeline. And then of course the last part of this chapter will focus on compiler enhanced techniques for enhancing ILP, parallelism, reducing the number of instructions, etc.